So where were we? We were talking continuity. Remember last week we started off by talking about the three criteria for point continuity, and then we left off talking about continuity on an interval, which is easy. Once you know how to determine whether functions are continuous at points, it all flows pretty easily from there. We say that a function is continuous on the open interval. And what's that mean, by the way, an open interval? What's specifically, what about the interval is open? What makes that interval an open interval? What makes that an open interval as opposed to a closed interval? Okay, and what does that mean? What's that mean about the endpoint, about the ends of the interval? They're not included. There you go, right? They're boundaries, but they're not included. Make sense? So it's all the values between A and B, not including A and B. Okay, so which is a little bit odd if you think about this. This poses a conundrum when we try to reconcile that definition with our informal definition of continuity, which, remember, that was just if I can put my pencil down at one point and graph the function without ever having to pick my pen off the board. If I can do that on the entire interval, then the function is continuous on that interval. Okay, I'll leave you with a little thought here, though. Where do I put my pencil down? Like, let's just say you understand the dilemma? Like, if I'm saying that a function is continuous on the interval from 1 to 5, where do I put my pencil down? My pen. At what x value? Are you suggesting 1? Was that a sly way of suggesting 1? Okay, what's the problem with that? It doesn't include 1. So I go, what do I pick? The point next to 1 then? What's wrong with that logic? Say that louder. Right, okay. But what is that number? Like, if I want to pick the point next to 1, what is the point next to 1? Yeah, it's, what do you think it is? 1.00001 maybe? Well, of course not, right? Because there's an infinite number of points between that number and 1. Is there a point next to 1? You can't define one, right? And this, it goes back, how many times have I done this little example here? It goes back to this all the time. If I cut my distance to the door in half every second forever, I never get to the door, right? So therefore, there is no point next to the door, because when I think I'm there, I've actually got an infinite number of points still between me and the door, right? That's a brain twister. Okay, there's a way around that, though, that we'll discuss when we're graphing this on the board. It's pretty easy to sidestep that. We can use some little tricks that help us out. We'll get there. So, continuity of polynomials and rational functions. This is the last thing we said, I believe, or almost the last thing we said. Polynomials and rational functions are always continuous at every point in their domains. There's never an issue. The only deal is with rational functions, we have to figure out what their domains are. We might have to exclude some values. For example, what about this guy? Here's a rational function. State the intervals over which this function is continuous. Okay, the easiest way to state the intervals where a function is continuous is to find the finite number of places where it's discontinuous. You guys told me the answer to this, I believe, before we left on Friday. At what values of x is this function discontinuous? 0 and -2, right? How come? Because those are the zeros of the denominator. Everybody give me thumbs on that. Does that make sense? Okay, good. So this function, so we could say f is discontinuous at x equals 0 or -2, right? So then on what intervals is it continuous? How would we say that? Those are the only two places where it's discontinuous. So what are the intervals where it's continuous? Using interval notation, how about? Everywhere else, right? How do I say that? How do I say every other x value except those? The best way to say it, in my opinion, is just to say this. This isn't what they're asking for, though. X is not equal to -2 or 0. That's the most concise way to say the domain, right, where it's continuous. How would I say every place except that? Doesn't that make sense? You got an idea? Did I hear something? Nope. Does that make sense? It would just be those intervals, right? The interval of all values less than 2, or the interval of values between -2 and 0, or the interval of values greater than 0. That's all of the infinite values except those few breaking points. We used commas. I could also use, being as I'm using interval notation, remember this, I could also use the union operator there instead of commas, either or. Okay, you see what I'm getting at there? Okay, not a big deal. All right. Okay, determine the points at which this function is discontinuous. Help me out. What am I going to do? Probably the first step here. See if I've trained you how to think about these composite trig functions. What do you always do first? Yeah, write it in terms of simple ones, right? Basic trig functions, sine and cosine. Secant is reciprocal of what? Cosine. Okay, good. So we get 6 divided by cosine of 8x. Okay, that helps, right? Now, what are the kinds of places where this function is going to be discontinuous then? Which red flag is popping up here? What are you seeing about this that's saying, okay, red alert, there's going to be some problems? Don't worry about the 8x part. Just ignore that for now. I don't want specific values. Just be very general here. Just tell me, like, what's going to cause problems that's going to lead to points of discontinuity? Hint, hint, hint. Where is that cosine function in the fraction? Oh, it's on the bottom, right? Okay, what's the problem potentially with the denominator? What value could the denominator take that would be very problematic? Ah, okay, right? So really what this boils down to is the zeros of that cosine function are going to be problems, aren't they? Those are going to be the discontinuities. What kinds of discontinuities are those going to be, by the way? They didn't ask this, but I'm asking you. What type? What do we got going on there? Are they going to be removable or non-removable? Okay, don't even answer that one then. You guys are kind of snubbing me today a little bit, aren't you? So what it? I mean, you don't have to even couch it in terms of removable. What did I hear? Yeah, you're right. How come? What are they? Are they jump? What do we call that? Because like where cosine is when I have zeros of cosine, what's on top always? 6. Okay, so if cosine were equal to 0, I would get something of the form a number divided by 0. What does that always correspond to? Yeah, vertical asymptote, right? So those would be infinite discontinuities, right? Vertical asymptote type. Okay, so we know we're getting vertical asymptotes. How are we doing so far? Any questions on that so far? Any clarification needed? Right, remember, like if we were, we can't directly plug in the values that are going to make the bottom 0 because the function's undefined there, right? But I could take limits as we approach those x values And the limits would either approach positive or negative infinity, wouldn't they? Right? Okay. So we know we're getting vertical asymptotes. All right. So now we need to figure out where those are happening, right? Wherever cosine equals 0 is where those vertical asymptotes will occur. So how do I set up some kind of an equation that's going to let me figure out the x values where that's happening? And I'm going to give you a big hint. No, we don't have to do anything fancy like that. You got an idea? What do you say it again? Okay, you guys are making this a little too complicated. Now, let me rephrase the question because I think maybe I just didn't ask the question very well. I just want to know the places where we're going to have vertical asymptotes. That's where the denominator is equal to 0, right? So I want to know where is, let's start off with this question. Where is cosine theta equal to 0? And that's a unit circle question. My hint was going to be I was going to draw a unit circle. It always goes back to unit circle, doesn't it? So where is cosine equal to 0 on the unit circle? Okay, here and here, right? Cosine is the x coordinate on the unit circle. X coordinate is 0 at the top and bottom, agreed? So it's going to be here on the unit circle, it's going to be at these places, right there and right there, right? Okay, so then I heard the answers pi halves and 3/2 pi, right? Partial credit. Only problem is there's an infinite number of other places. What do I mean by that? How is there an infinite number of other values where cosine theta is equal to 0? If I were to graph a cosine function, if I graphed something like y equals cosine theta, wouldn't I just get something like this? How far does that cosine function go? Infinitely far. Well, how many places is that cosine function equal to 0? You guys picked out 2 of them for me. Oh man, what the heck? Is that it? Yeah. You guys told me that point and that point, which are x coordinates of pi halves and 3/2 pi, but there's an infinite number of other spots. Agreed? Give me one more example. What's another angle where negative pi over 2, that's right there, absolutely. What's another one? Negative 3/2 pi, there you go. Okay, we see all those on the unit circle too, right? On the unit circle, think about the conventions. We sweep out area, positive area is swept, or positive angle is swept out in the counterclockwise direction, starting there, right? An ant walking on the unit circle would have walked positive pi halves, positive 3/2 pi, positive 5/2 pi, positive 7/2 pi, or he could have gone backwards. He could have just swept out angle in the negative direction and walked backwards around the unit circle and gone negative pi halves, negative 3/2 pi. What do all those seem to have in common? Negative 3/2 pi, negative 1/2 pi, positive 1/2 pi, positive 3/2 pi, positive 5/2 pi, positive 7/2 pi. There's a trend. What is it? What's the trend there? Okay, they're adding, right, okay, sort of like adding 2, well, kind of, right? We're adding 2 pi to the numerator, right? If I look at those numbers again, here's a list, and it goes on forever and ever. When pi is equal to what? Well, it could have been, we did negative 3/2 pi, negative pi halves, positive pi halves, positive 3/2 pi. Let's put the pi on top here. That might make it a little easier. Yeah, I like that. Ooh, I like that one. That's good. do it this way. So yeah, whatever the number that's being multiplied by pi halves is increasing by 2, isn't it? Right? Agreed? What else about those numbers is consistent? Over 2. They're all odd. Yeah. Aren't they? How could we describe that? Aren't those just all of the odd multiples of pi halves? Everybody agree? Okay. Okay, so now we're getting somewhere, right? We got odd multiples. All this, we're just saying all of the odd multiples of pi halves. Right, so if we wanted to kind of build a recipe for this, the recipe would be that we're going to have every element of the set of odd integers is going to be represented times pi halves. Okay, so now the next question is, how could I specify? How could I write out that set? How could I write out something that represents all of the odd integers? Because that's really what it is, odd integer multiples of pi, right? I should write that down here, shouldn't I? How could I write that out? I'll get you started. Let's define something here. Let's define n is every element of the set of integers. So n is, in other words, n is an integer. Okay, now you did something even more complicated, right? You did something, no, that you're right. But let's just figure out how I could say, let's write it this way. When theta is equal to something times pi over 2, I want you to fill in the blank there. It's an odd integer, right? I want to represent an odd integer times pi over 2. That's all it is. That means the odd multiples of pi halves, right? If n represents an integer, every element from the set of integers, n is, -3, -2, -1, 0, 1, 2, 3, etc. How could I somehow get this list in terms of n? I can't just put n there, because n pi over 2 would mean every integer times pi halves. I only want the odd ones. If n is an integer, then how do I say an odd integer? How would I say an even integer? If n is an integer, how do I guarantee I'm getting an even integer? Okay, I'm not letting this go. You guys are going to get this. I feel like I'm probably not, I don't know, somehow I feel like I'm not. So here's the set of integers, right? The set of integers looks like I want you guys to give me now the set of odd integers. No, even, sorry. Let's do even. Even's a lot easier. Once we get even, we'll get the odd ones easily. What would I have to do to each of these integers to create an even integer? What would I do? Well, okay, in fact, I could multiply by a specific number. 2, right? If I double an integer, I'm guaranteed to get an even integer, right? Look what happens if I double all these. If I double 0, I get 0. If I double -1, I get -2. If I double -2, I get -4. Right, you get the idea? Right, everybody agree? Okay, so then if I'm saying this is the set represented by n, the set of even integers would be 2n, right? So how could I say the set of odd integers then? What could I do? 3n. Okay, if I multiply by 3, I'm not guaranteed to only get odd integers though, because 3 times 2 is 6, right? Good idea. How are the odd integers different than the even integers? They look pretty similar, right? The gaps between numbers is always 2, but they're just offset a little bit, aren't they? There you go. I could either do 2n plus 1 or 2n minus 1, right? You get that? Right? Well, if the set of even integers, if n represents an integer, right, then 2n represents an even integer, where n could be any integer, right? Agreed? Okay. So the odd integers then would just have to be offset from those by 1. To make an even number odd, I just subtract 1 from it, don't I? Okay, so the set of odd integers, and I don't want to write this whole thing down. It's just going to give me 2n, that's an arrow, 2n minus 1. I could do 2n plus 1, but we always do 2n minus 1. For some reason, that's just the way the textbooks always do it. Okay, so then let's go back here. So if n is an integer, I want the set of odd integers. That's just going to be 2n minus 1, the quantity 2n minus 1 times pi halves, right? That's it. Those are all the values that theta could not have, because it would cause cosine to become 0, right? Okay, the only problem is these aren't thetas. What are they? Cosine theta equals 0 when theta equals quantity 2n minus 1 times pi halves, right? But what is theta? I'm not feeding cosine thetas. I'm feeding it what? 8x's, okay? All right, so then the condition is this is going to be discontinuous when, if I combine all this stuff, I'm going to get when 8x is equal to 2n minus 1 times pi over 2, right? Everybody see that? Okay, so what I want to do is I want to solve for x, because I'm feeding the cosine function angles based on 8 times x. I want to know the values of x that I'm going to have to exclude, because this is a function of x, not theta, right? I just have to solve that thing. Well, that's easy to do. What do I do to solve for x? One step. Divide by 8. So x, what I should say is x cannot equal, right? X cannot equal 2n minus 1, quantity 2n minus 1 times pi over 16. That's one way of writing it. That's fine. Those are all the values that we have to exclude, okay? We could, now what Carson did, which was kind of cool, is he essentially, like he was, I think you were on the right track with this. He was just writing this as separate terms. He was thinking of it a little bit differently. We can still do that. I could just distribute the pi 16ths to each term, couldn't I? So I'm going to get x cannot equal, let's see, that's going to be pi over 8, pi n over 8 minus pi 16ths. That's another way of writing it. Either way, it doesn't matter. How many values are represented there? How many integers are there? Because n represents all possible integers. An infinite number. Yeah, and if I look at the graph of this thing, that's what it looks like. Well, there are an infinite number of asymptotes to that function, aren't there? Right? There's one there. What's that one at? Well, it looks like it's at between 0 and pi 8. So that would be pi 16ths. Yeah, that makes sense. That's going to be the value when n is equal to 1. Right? When n is 1, I would get pi eighths minus pi sixteenths is pi sixteenths, right? What's the next one going to be? First one was when n equaled, what would the next asymptote be at? N equals what? 2, sure. Okay, so what about 2? If I plug 2 in, I'm going to get pi times 2 over, that's pi fourths, right? Pi fourths minus pi sixteenths is 3/16 pi. Yeah, what do you know? At 3/16 pi, I'm going to get, that's halfway between pi eighths and pi fourths, there's going to be another asymptote, right? If I want to go the other direction, I started with n equals 1. What if n is 0? Well, if n is 0, I'm going to get 0 minus pi sixteenths. I get negative pi sixteenths. Sure enough, there's an asymptote at negative pi sixteenths right there. Okay, that makes sense? So we just said an infinite number of asymptotes, and we were accurate. It's that infinite set of asymptotes right there. This says all of them. These are the values that x cannot have. X cannot be n pi over 8 minus pi sixteenths when n is an element of the set of integers, when n represents a set of integers. Okay, that's pretty cool. We can do that, right? Now, if we had, a lot of times you guys will see problems like this where it'll say on the interval from 0 to pi or something. Okay, well, just find the values of n that give you values of x that are between 0 and pi. Just plug in values of n to give you all those, there's only going to be a handful of them, right? Those are the values between 0 and pi that you'd have to exclude. Okay? Make sense? Okay. All right. That's a really important thing. You guys probably did some stuff like this last year, I'm guessing a little bit, maybe, hopefully a little bit. Okay. But that's a really important thing to be able to do. That's why you guys were saying that. Okay, yeah, it's right. Now, a better way to think about that than is to do it in terms of the set of even and odd integers, like we did here. That's a much more natural, intuitive way to think about it. Okay. What about here? Continuity on an interval. Then, okay. So, if we're going to define continuity on an interval, we talked about an open interval. What if we want to actually talk about a closed interval? That would mean we would have to include the endpoints. We didn't include the endpoints when we talked about an open interval. So in order to do that, we need to add another tool to our bag of tools here in calculus. We've got to be able to talk about continuity at an endpoint, right? Now, if you think about that, if I'm on the, like, here's a picture, right? Here's our function. So we're going to do something like this. We're going to go from A to B, right? How am I going to define continuity at the endpoints A and B? Because you can only approach those from one direction, right? So what did we say last week about continuity at a point? In order for it to be continuous, it had to meet 3 criteria. The function had to be defined at that point. Well, that's easy enough, right? Is the function defined at its endpoint? Easy enough. The function had to have, the limit of the function had to exist at that point. And then finally, the value of the function and the value of the limit had to agree, right? Okay, well, last week we were always talking about points that were not endpoints. And so the limits were two-sided limits. What do you suppose we're going to do differently here if we're talking about endpoints? Can we have a two-sided limit at an endpoint? No, it doesn't make sense, does it? Right? Because you can't approach A from the left, you can only approach from the right. And you can't approach B from the right, you can only approach from the left. Right? So the only difference is going to be when we define continuity at endpoints, the limits are just going to be one-sided limits. No big deal, right? And so we would talk about continuity from the right and continuity from the left. Well, what's it mean to be continuous from the right? That would be if the value of the limit as x approached a from the right equaled the value of the function at a, right? Continuity from the left would just say that the value of the limit of the function as x approached a from the left would equal the value of the function at a, right? Okay, so then we can put this stuff together, add those ideas, that new idea, to what we said a couple minutes ago about continuity on an open interval, and we could expand this and say this part right here. Okay, look at this part right here. Lost it. Where was it? Oh, here we go. So we talked about continuity on an open interval. Analogously, a function f of x is continuous over an interval of the form, we'll do the whole thing for now. Of the form a semi-open interval, right? We're including the right end point but not the left point. If it's continuous on the open interval from a to b, and it's continuous from the left at b, because that's an endpoint. That's the right endpoint, right? Or we could say it's continuous on a different kind of interval. How would we say it's continuous on that kind of interval? In order to be continuous on that interval where we're including the left endpoint but not the right, what would have to be true? So a function is continuous on this interval if what? There's two parts. I'll get you started. It's continuous on the open interval between the endpoints, and what else has to be true? You mean a from the right, you mean, right? Okay, good. Then that limit would have to equal the value of the function there, right? So part two would be, it would have to be continuous at a from what direction? From the right. Agreed? See how that works? And then we could say in general, continuity on the closed interval from a to b equals two things. Continuity at every point between a and b plus continuity at the endpoints, right? What's that look like? Well, continuity on the closed interval, f of x is continuous on the closed interval from a to b if and only if, that's what that IFF means, right? If and only if. How do I say continuity on open interval? Well, just say it. F of x is continuous on the open interval from a to b, and remember that's, well, I guess we just said and, that's fine. And continuity at the endpoints, what's that mean? Two things. Continuous at the left endpoint is continuous, so that's it. At a, it's continuous from what direction? From the right. Okay, and wouldn't I say that like that? Right? The limit of the function as x approaches a from the right is equal to f of a, right? Okay. And has to be continuous from the left at b, which is just this. The limit of the function as x approaches b from the left equals the value of the function at b. Okay? Give me thumbs on that. Does that make sense? Okay? Okay? Getting there. I mean, it's a lot. So let's practice this a little bit. You guys tell me, based on this graph here, just conceptual practice. F represents the blue and the red graphs combined. I just broke it into, I color coded it for reasons that will be obvious to you. It's discontinuous at A and B. Give me thumbs on this. First question is f of x continuous on the open interval from A to B? Give me thumbs. I'm seeing some thumbs down. Any thumbs up? Are there any places on the open interval where I'd have to pick my pen off the board? No, there aren't, are there? Now, what you're thinking is, where would I put my, I know what you're thinking here. You're thinking, there's no place to put your pen down probably, right? Is that what you're thinking? Okay, sure, okay. I'll give you the benefit of the doubt. Well, mathematically, that just means that we're going to, like if I want to represent an open interval, it means I'm just going to do it like this. Yeah, let's talk about that for a second. Okay, so okay, here's an example of a function that is continuous on the open interval from A to B. In reality, there would be there's no way I could graph this exactly because there's no place for me to put my pencil down on the board or my pen down on the board. I could never pick an appropriate starting place. But I can get around that by doing this instead, right? Whoops. There, I graphed it. What does that open endpoint mean on that interval? Okay, it means it includes everything except that point. So there, I graphed it, right? I just graphed a function that's continuous on the open interval from A to B, okay? So would this one work also? Oops, different color. Oh, come on. Different color, I said. Sure, right? Because the red interval contains the endpoints and the open interval in between. So this function is also continuous on the open interval, right? See what I'm saying? Okay. All right, we'll wrap this up tomorrow. I'll be sure to put this video and notes up because I imagine there might be some people looking back at this one to ponder this a little bit.